Alrighty then, it's 6.8, 6.9, 7.0, and 7.1. And this will be scheduled to be seen on November 2nd and 3rd, Election Day for many of you. And this will be concluding the coverage for the second exam, which is scheduled for November 9 or 10. And we'll have a review live on Wednesday, Thursday of the following week. And we'll get into the material now and finishing up chapter 6.8 and a couple of sevens that just to keep pace with the material so we don't get behind before the final. Well, anyway, by now you see why normal distributions are often good models of error, because we aggregate the forces and how we might use them to make predictions. But why is it that distributions that look very different from one another are all called normal? Well, we showed you four different kinds before. And let's see if I can stretch the screen. Of course, it won't let me do that whenever I want to. Anyway, I'll see if I can magnify it later. Let's consider what that really means. It looks like a bell, kind of, a narrow bell or a wide bell. And here we have Bargle and Cargle, and Gargle and Zargle, and all the stuff they talk about their video games. I've never heard of them, but anyway, here we have a narrowly distributed distribution with scores, apparently whether they're high scores or average scores, whatever it is. The Cargle is much more spread out. And so we see these blue lines meaning the mean, which they'll describe, and the red line meaning a number that they're trying to beat. So we're trying to see about the mean of what, 35,000. And we'll still have some Halloween music on here. And I'm trying to see what would be larger than, what probability would be greater than 37,000, something beyond the mean. And the narrowly distribution, the narrowly very small standard deviation here, very low variation, it would be tough to get above 37,000. And the widely dispersed data, Cargle, it would be relatively easy to get above 37,000. Not quite up to the 50-50 level, which would denote the entire right half of the curve, but somewhere maybe in the 40% range. Editing out, of course, this little window here that's above the mean, but yet still less than 37,000. Might have been helpful if they'd put some numbers down here. In fact, now that I have a tool that lets me write on the screen, I could probably do that, but since I have to do so much erasing, I think I'll withhold that until it becomes a little bit more, relevant. So anyway, we have those two games. These two distributions look pretty different from one another, but they're both normal distributions. They have the same general shape in that they are considered to be, in the long term, a normal distribution, a bell-shaped distribution. They're roughly bell-shaped. And there are way more scores in the middle than there are on the tails, and they're also symmetrical. Those are characteristics of our bell curve. And they're very regular, they're very quantifiable, then that description would seem to indicate. Oh, I just can't seem to widen this out at all. I don't know what the deal is. But anyway, okay, I'll try not to be distracted by that. If we look at zones that are plus and minus one standard deviation away from the mean, we can call it zone 1. And once we find out what the standard deviation is, we can actually plot that. So if they're saying, of course, as we said, the mean was 35,000, but now we're going to say that the standard deviation is 1,000. What's the range of scores in what they called zone 1 in Bargle? Let's just plus and minus 1,000. And sketching a picture or looking at the prior picture might be good. This is 35,000, and we go only to 36,000, maybe back to 34,000. That would be the zone 1. Which was it, Cargle or Bargle? I lost track. Bargle. Okay, so Bargle would be 36,000 there, 34,000 there. So a big chunk of change right there in the middle, huge amount. But if it's standard deviation of 5,000 for the second distribution, well, that's a different story. So 5,000 takes us all the way up to, well, 35,000. That's an easy one because it'd be 30,000 up to 40,000. All you do is take your 35,000, which is supposed to be here, add 5,000, there you are, 40,000. Subtract the 5,000 from the 35,000, you're down to 30. So we have a big wide area. Turns out that that's going to tend to be the same. We'll show minor differences as they start to collect them. But they divide the zones up, and they'll show more physically what's going on. And I have the red line and all. They transferred each person's raw score into a z-score, indicating how many standard deviation a score is away from the mean, whether it's above or below. And we coded it a 1 in the variable and try to get this sort of an orange zone. I guess that's orange between plus and minus 1. Purple would be outside of zone 1, those that are more than 1 standard deviation above the mean or less than minus 1 standard deviations away from the mean. And similarly down here, it just looks like more spread out because, as you see, 5,000 does take it quite a ways away from the mean on both sides. But it's still going to be the same area, the same probability, believe it or not, with very minor differences. As they start to collect them, they use a tally command. They are looking at the various commands here, proportion, format, and look how similar they are. May not look like it at first glance, but each time zone 1 is right about 68%. This is raw data, so it may not be the exact theoretical number that's presented, but look how closely they are to agreeing with each other. And then, because it has to add up to 1, there's no third option. These outside the zone 1 have to also agree as well. They're both off by just about 0.002 if you look at the raw difference between the two, but that's unimportant. They're just very close together. And they're very similar, about 68% for both Bargle and Cargill. Interestingly, more than half the distribution is within 1 standard deviation of the mean. Okay, there I got to zoom. Well, my pad is just getting worn out, I guess. So let me close it up so you can read it. What's the range in z-scores for the data points in zone 1? We just mentioned that. In zone 1, it'll be in between the ones, not greater than a... Yeah, well, there we go. That's one way of saying it. Not the way I would have thought of, but it does matter, and it does make sense. Greater than 0, what's that all about? Less than 0, what's that all about? 0.5, 2 and minus 2? None of the others are even close. A, which is pointing in the right direction in between the numbers, that's what we're looking for. So should let you do that on your own. Okay, 1 standard deviation in the positive direction is z equals 1. Negative direction, it's minus 1. So between those two numbers, we have our values we're interested in. This time, they've decided to change it up and talk about 2 standard deviations and using very strange color combinations. If we're looking at within 2 standard deviations is the big green zone, and outside of that is a purple zone, both on the left and on the right. And then we expand this from the narrow one to the wide one, Cargill, and yeah, we still see a big preponderance of values in between 2 standard deviations, which, by the way, if you take 35,000 as your mean, and we add in a couple of standard deviations of 5,000 each, well, 2 by 5,000 is 10,000. 10,000 plus 35,000, 45,000. Take your 35,000, subtract that 10,000 we just talked about, and we're down here to 25,000. It all seems to be measuring up pretty well. And surprisingly, may not look like it, but the area in the green zones are the same, and the area in the purple zones are the same in the long run, except for minor differences. Now, Zone 2 consists of most of the distributions. What do you think they may be? Well, make your best guess. One of these is very close. I'll just let you figure that out, but then of course we give you the answer pretty much right away, and there it is. They're very close together, both around the 95% mark. And then outside of that would be roughly, well, 100 minus 95 is 5%, or if you'd rather, 1 minus 0.95 is 0.05. So being outside the other color would be outside the two, and they're both very close together, as we expect. So basically 95% fall within 2 standard deviations on either side. So if you get just 2 standard deviations away, you've got 19 out of 20, 95%. That's approximately, of course. So when you get to 3 standard deviations, what do you think it might be? Well, we already hinted that the tables run out at about 3.5. And one could imagine taking 3 of the 5,000s to go 15,000 away. That'd be 1, 2, 3 leaps. The graph paper here works out perfectly. So you'd have to take it out to 50,000 on this side. And in the center, 35,000 minus 1, 2, 3. That would take it out very briefly to 20,000. We're not going into the exact calculations here. We're just showing you that it just widens it even further. And there isn't very much left beyond those key numbers of 20,000 and 50,000, which they're going to show you in just a minute anyway. I just thought I'd preview it. So it's going to be almost everything. And so now we look at 3, both on the narrow distribution Bargle and the wide distribution Cargill. And if you look very carefully, especially if you zoom in, you can see just a little hint of purple there. Same with this, a little bit of purple on the outsides, the tails as they call it. And yeah, it's very, very, very wide. And they've decided to group them all together. Here's the zones, zone 3 especially. Look how much that is. It's not all of it, but it's getting real close. And then you subtract this number from 1, and you get what's outside in the tails. Yeah, very little left, very little. So, yeah, almost everything and then almost nothing. And we don't even consider 4 standard deviations because you have to get out lots of decimal points for that one, which is why we don't really go much past 3 in the real world. And so this empirical rule kind of gets this all together to 2 decimal places on the percentage, or if you just wanted to use 4 decimal places on the proportion, like they did here, same difference really. But 68, 95, 99, 7 rule is certainly one of those things that can happen. And instead of saying 68, here's the full details, 68.2 cents, 26% in the long run, 95.44% in the long run. And this one is actually quite helpful to us because we can't round this up to 100%. We've got to keep it a little less than 100. So it's 99.73. And 99.7 if you wish, depends on where you want to round it, but you can't just say 100%. That wouldn't really help us because there is that little glimmer of stuff that's outside. This has been exaggerated. It's not quite that wide. Same with this one, that's even more exaggerated, but consider this curve probably is flattened out a little bit more, but there's a little bit of stuff out there. So in other words, out of 10,000 occurrences, 27 of them will be either here or here. That's not many. In fact, if you want to find exactly how much, you'd have to divide the 27. And I got this by subtracting it from 100% and then putting it over 10,000. So you've got 9,973 that are within the threes, but only 27 as you subtract that from 10,000. As I already moved the decimal over, you would only have 27. It would be about 13 and a half here and 13 and a half here out of 10,000. That's a lot. A very tiny, tiny number is what I'm trying to say. So the smooth normal distribution, something that is so perfect it doesn't really exist. Just like straight lines. There are straight lines in the world, but a mathematical straight line, this is a very good analogy, it's a perfect thing that has no mass, it's infinitely thin, no jitter, doesn't bend, and it goes on forever. So the same thing here. Mathematical or statistical normal distribution is perfect. No mass, no jitter, it goes on forever. So in other words, what they're saying is this is asymptotic and that never touches down. It's like an airplane that never quite touches the ground. It gets closer and closer and closer and closer, or even over here. But it never quite touches. So we do have room for -4, -5. Standard deviation of, or z-score of 80. Yeah, I actually saw a z-score of 80 once. They were trying to compare telephone usage of today with telephone usage of the 1920s, just about 100 years ago. It was about 90 years ago when I saw this example. And yeah, z-score was, yeah, it was measurable, but the probability of something like that being the same was incredibly rare. And no, there's no way that we could compare today's usage of cell phones with any kind of phone they may have had just about 100 years ago. It was just crazy to even think of that. So that's why the z-score got completely crazy. And it is an exponential number, essentially. So anyway, or beyond that even. Okay, so we have, could measure, for example, the one they give, somebody's thumb length of 1,000 millimeters. Whoa, that would be, I guess, 1 meter, right? So that's a pretty big thumb. Have to be a pretty big giant. And yeah, we could put that, kind of like telephone usage of 100 years ago compared to now. No comparison. And so here, this person would stand out as being extremely large, maybe a z-score of who knows how much, 20 or 30, something crazy that would be extremely, extremely rare. and yet not technically impossible. It's kind of like winning the Mega Millions 3 weeks in a row or something like that. I mean, it could happen, but would it ever? No, not really. Okay, we can change the standard deviation to whatever we'd like it to be. Notice this is a very long set of our code. What fun. So we could just run it, but they've already run 3,500. So what I'm going to do is I'm going to change this to like 3,000, and we'll kind of compare the two. That's not much of a change. But if I go ahead and run this, we'll see what happens. We get 3 different graphs. What I picked was a standard deviation that isn't quite as large as what they have. So these should be rather similar, So they picked 3,500, and it's a little bit easier to read. But it's a little bit more spread out. Mine's a little tighter. And theirs is even more spread out than mine. And what they've done here, by the way, is they've looked at zone 1, zone 2, zone 3, which is a nice way to put it. The red zone is between plus and minus 1 standard deviation. And then the green zone builds on that and takes it even out to 2 standard deviations. And the 3 builds on that and takes what's already there and takes it out to 3 standard deviations. If you can see any purple stuff, that's outside the 3s. And that is very rare, only 27 times out of 10,000. Or 3 times out of 1,000, if you'd rather put it that way. And mine looks very close to that, Mine just a little bit tighter. It might make it a little bit easier to see these wider distributions here. And they've got a new game called Zorgle. Oh boy. So that's the plots there. And our console probably doesn't have much in it. Oh yeah, there it is. It's got the data. And these numbers are pretty close to what we thought the empirical data would be. 95%, and these are close to 95%. 99.7, these are all pretty close to that. And 68 point, whatever we said, 68 point, what is that number anyway? 68.26. Okay, these numbers are close enough. They're not meant to be exact. They're just kind of samples from something we know to be true in the long run. So you can pick any number you like, and we encourage you to do that. But if you start picking more and more numbers, it may start to overlay. So you may have to refresh and redo it. So I tried it, and it started to become a little bit hard to read. I think it's kind of an accumulation or something like that. But you can also discover more about our commands if you'd like. We're not really teaching some of these others, though. Okay, so they got something like that. They got more decimals than I did. I'm not sure why they went from 4 to 4 to 5. I only got 3 out of mine. I'm not going to take the time to look at the decimal command right now. This empirical rule can be very useful when trying to make a quick interpretation of a specific score. If a friend has a baby and tells you it's 54 centimeters long, how would you interpret that? As an experienced statistician, you should ask, what is the mean? And what's the standard deviation? And they're saying that the mean of baby in terms of centimeters now is 50 centimeters, standard deviation about 2 centimeters. So you could say, wow, your baby is like 2 standard deviations above the mean. How'd they get that? Well, 50 plus 2 more does give us 54. Didn't break out a formula, I just did it intuitively. Oh, you could use the Z formula if you'd like. But it says you'd be slightly wrong. Here's that part's not wrong, but the statement here that only 5% of babies are longer than 54 centimeters, that's not really true because we have to look at both sides of the coin. We're roughly calling that 95%. And if there's, say, about 5% outside this window, well, it's not going to be all clustered at the top. It's going to be split evenly. It's going to be split in half. So roughly, not just 5, but 2.5% here and 2.5% there. In other words, there's only 2.5% of the babies that are larger. That's even a stronger statement than before. So let's see how they describe it. And we'll review in case I went too fast. If 0.05 of the scores are outside the plus or minus 2 standard deviation, zone 2, half of those will be expected to be more and half would be less. So it isn't just 0.05, it's half of 0.05, approximately, of course. You get more exact than this, but 0.025, the top 2.5% would be higher than the zone 2, the 2 standard deviations above the mean. So it's even more impressive than we thought. He or she is even longer than 95%, 97.5% rather of all babies. So that's pushing them into the 97th percentile instead of the 95th percentile. For those of you who have checked, SAT scores or something like that. What counts as unlikely? Well, there's different interpretations, but generally speaking, we do talk about, well, let's see, they've got finding a model of finger lengths to design stretchy, one-size-fits-all gloves. How big should we make the gloves? Very long thumbs are unlikely. They're still possible. If we make them too big, though, then we'll alienate the short people. So you got to find a balance there between helping out big people and helping out small people. You can't make them too big or too small. What would be the right glove size? So looking at what's unlikely is a very helpful thing. Okay, one could say that it would be in the 1% range. But, you know, well, anyway, let's just go ahead and get to the point here. You can read that part. But 0.05 and lower probabilities are considered unlikely. In other words, if it's less than 5%, 5% or less, that's called unlikely for most people. Now, if they're going to say something else, they will let you know. Sometimes you can do the 1% level, you can use a 10% level, but most people will pick a 5% level. That's what we will do here. Get to a probability that's less than 5%, we'll call it unlikely. Get a drink of water here, excuse me. So that's how they're going to do it, and 5% is a pretty low likelihood. And that also pretty much, although not exactly, but close enough right now to get to the zone 2. Zone 2 keeps the 95 and change percent in the middle and 5% on the outside. So those unlikely 5%, considered to be by the gray lines, here is a gray line here, throws out the bottom 2.5%. This gray line here also throws out the bottom 2.5%, top 2.5%. So upper 2.5%, bottom 2%, together 5% thrown out, 95% in the middle. Here's the curve that's supposed to go over this messy set of data. 95% in the middle. We've got zone 2, basically. One could get real exact. Maybe later we'll talk about 1.96, but you'll notice that number is close to 2. We'll just use 2 for now. I've seen stats classes that just use 2 the entire way. So now it's up to you, and a few people who have tried this already weren't so good at it, but the idea is just to see what's likely and what's unlikely. Choose all the unlikely thumb lengths. In other words, what's to the right of this gray line? What's to the left of this gray line? Not the stuff in the middle. That's the typical likely stuff. That's the stuff that will happen regularly. This stuff will not. Neither will this stuff. It's too low, too high. So you find some numbers, I will let you do this, that are either too low or too high. Not the stuff in the middle. Certainly 64, here's a clue. That will not work. It's way too close to the mean, which looks like it's 60.1 as I recall. Okay, so then we have this funny way of saying it. Yeah, I'm not sure if I would say that. But anyway, that's fine. Pick numbers that label the regions below with the appropriate proportion. So in other words, find out what's in the tail and on each of the tails. I would do the tails first, and those will give you half of the 0.05 that we were looking at. I'll just give you that clue. And what's in the middle has to do with the zone 2. What was in zone 2? Rounded to 2 decimal places. And I'll give you that clue as well. So all you do is just scroll back a little bit and see what we were talking about. It wasn't exactly the 95. But let's go ahead. You would submit this, of course, when you're done. Please don't forget to do that. Be sure you do it before the test. Okay, we have a very short 6.9, and this is why I'm going to go into Chapter 7. Let's summarize where we are. We've developed the idea of the mean as a model, developed some stats that quantify the amount of error around the model. We've shown that the mean is the point of the distribution where the square deviations are at their lowest level. So we like to minimize that number, which has to do with the variance and especially the standard deviation. And we could also think of the square deviations from the mean as the total amount of variation left after we take out the mean. And that's the unexplained variation. The error is still left in our model. That's random chance at work. And is as low as we can get without adding another variable. But in Chapter 7, we're going to add an x variable. Imagine that. We're going to have 2 variables like what usually happens. I'm frankly not used to seeing all this time spent on what they call the empty model. Normally we just pass over that rather quickly, spend a few minutes on it, but here we've spent a good deal of time on it. It's just a different way of looking at it. So we're going to do just that, come up with something that summarizes the main ideas in the chapter, and that's an instructive tool for you to recoup what you've learned, and it will help you on the test. We've just spent, just a few minutes ago, some time talking about the upcoming test, and so the questions are coming together and all. So here's some review questions. I'm not going to go through them now, but that's something you need to do before the test, and that would be before November 9 and 10, whatever day your test is. So sure you do that. There are two parts. One of them is more heavy with the R and the other one is not. Let me just go to the modules. And so definitely take a look at them. I strongly recommend you take a look at them and make your best guess. And if you got it wrong, learn from your mistake. Far more important than just getting some points on the quiz would be to learn from your mistakes. So remember, it'll be 1% apiece for each of those two quizzes. It has to be done before the test. So let's go into Chapter 7. I know some of you may resist this, and we're not going to be covering this on this exam, but I do need to keep pace. Otherwise, we'll be having to cram in. And this has actually happened. It was actually on the schedule. Cram 6 sections in to a 50-minute class. Wow. When I taught UC Riverside, this teacher was just out of her mind. And I don't ever want to do that again. I just soon. But it was in one of those classes like this where we have no choice. We have to follow the line. But on the schedule, let's just cover 6. And yeah, right. It was ridiculous. 10 minutes or less per section. Well, anyway, that's not happening here. We're going to get ahead of schedule. And this will not be directly on the test, but perhaps indirectly it could be. It does tie together pretty well. So it isn't like it's completely foreign to you. It doesn't hurt to learn a little bit about this in your spare time between now and the test. Okay, they're saying you may be frustrated. It's about explaining variation, but we haven't really done it we're just talking about the mean. So let's see. Let's start by explaining the variation. And here we have a male versus female situation with the thumb lengths. And as expected, as we've already seen, females' thumbs on average are a little bit smaller, shorter, I guess, than the males are. And you can see the red line mean there and the green line mean there. And it explains some of the variation in thumb length. It's a broad stroke, but doesn't explain everything. It doesn't explain why this person has 90 millimeters and this person has 45 or so millimeters. And it doesn't explain everything, but it's a nice first start, though. We can use that. It's a helpful thing, but it doesn't do everything. So that's the idea behind that, I guess. And so if you know somebody is male, you would make a different prediction of the thumb length than if you knew they were female. Yeah, so they just, you give a bit of a boost to the male's predicted thumb length. So that's the idea. We have thumb length equals the sex or gender plus the error. And it says that sex explains some of the variation in thumb lengths, but other things also affect thumb length. Building on the previous section, let's now try to say this relationship more precisely as a statistical model. And that was a fast section. This is why I'm going a little deeper into Chapter 7, because we didn't have anything to talk about there. So let's get into 7.1, specifying the model, reviewing what they like to call the empty model. And I don't believe any other book actually calls it that but they seem to enjoy that tremendously. And so as I'm trying to squeeze this down, very tricky to do that. Okay. We introduced previously an idea of a statistical model as a function that generates a predicted score for each observation. Okay, we wrote it like this in the general linear model notation, and so we can interpret this notation as y sub I equals b sub 0 plus e sub I in the case of our thumb data. And so we can say that the person's thumb, yi, is equal to, that is the length of the person's thumb length is what I meant to say, would equal the mean of everyone's thumb length plus each person's residual, each person's difference or error. That could be another word. Lots of words. I know it's confusing to put so many terms to everything. And let's move along. In the case of thumb length, I still need to squeeze this down just a tiny bit. And it just doesn't want to do it. Okay, and that's too tiny. Okay, that's better now. In the case of thumb length, the model states that the data represented as y sub I, which is each person's measured thumb length, can be thought of as having two components, the model B0, which in this case is just the mean, but they like to keep it general. They're so general here. And That could be called the grand mean. That's another name for it. And then the error, which is like the random chance aspect, each person's residual difference from the mean represented by EI. And then they finally explain grand mean. It's just the mean of everybody. They could have called it the mean, but now they're going to call it the grand mean because we've got the mean of the men and the mean of the women. And so they're going to kind of put it all together for overall grand mean, which would be like if you didn't even separate the gender out and just said, okay, you're a person, you have a thumb, period. There'd be more variability there. If you isolate their gender, there'd be less, but not zero variability. Okay, so let's see. We have some other things to look at. So tiny fingers, they use the head command. They found three. Well, actually, this is the tiny fingers. They didn't even have to do that. Just have 6 anyway. 3 females, 3 males with their thumb length in millimeters. And turns out all the females had shorter thumbs than the males. That didn't have to be, but that's the way it worked out here. And now representing it, broken down by gender, they had the faceted histogram, or they could use the scatter plot, and they have a quick R review here, GF point. And hard to say which is better. I don't really have a preference here. Maybe this one to me looks a little bit better, although they disagree. The females are all here, the males are all here. They all have heights of 1. It's silly to break out the y-axis because there's just a count of 1 in each case. So why would you want to even bother dividing that up? It seems silly. But anyway, over here, the scatter plot, we have the females that have their thumb lengths, and the scale is over here, and then the males are all above that. So they're saying exactly the same thing in a different way. So there's lots of different ways of going about it. Why are all the bars the same height on the left? Well, yeah, because the count is 1. All you have to do is read the scale on the y-axis and notice, yeah, they all say 1s. And we didn't have any duplicates, in other words. We might have, but we didn't. So in the histogram on the left, a bar has been circled. Identify the corresponding point in the jitter plot on the right. So here we have what looks to be a male, a little fuzzy, but that would be a male score. And so basically, I'm not going to tell you, but we know it's not in the female zone. It'll be somewhere in the male zone. So you should see if you can figure it out. Notice here we're going from left to right. Here we're going from bottom to top. I prefer to go left to right personally, but since they're making us choose one of these 6 letters, go ahead and choose wisely. They will tell you if you got it right or wrong. There's no penalty here. We just want you to do something. Don't leave it blank. That's the worst thing you can do, is leave this stuff blank. In the scatter plot, the grand mean of the distribution, ignoring sex, is represented by the blue line. So this is what they call the empty model. That's everybody's average. And the grand mean is the model prediction for observations under the empty model. That's the same thing. So if somebody is male or female, their predicted thumb length is 62 overall. That's just putting everybody together, which can be done. So each person's measured thumb length would be equal to 62 plus their error. That's pretty boring, but they seem to think that's fun. So each person has a deviation, whether they're female or male, and some females would be above average, some males would be below average, as we saw already. This one doesn't happen to show that. So those are the deviations or errors. And then y sub 1 for the first person is this person's actual thumb length. The average plus the residual or difference gives the actual deal, and that's the actual thumb length, which might be about, what, 55 or so? Yeah, about 55. But they're just breaking it down. It seems unnecessary to a lot of people, but they're just simply separating the mean away from the rest of it. That's all they're doing right now. Adding an explanatory variable to the model, that's the x value. So we're going to use this x as an explanatory variable, excuse me. We modeled the variation in thumb length with the 2 numbers. The mean for males, 65. The mean for females, 59. Notice those 2 would average to 62 with an equal number there. But now we're getting a little bit better at this because the mean for males is up here at 65, as we just said. There it is. Mean for females, 59. Yeah, it's a tick below the 60, so that's the kind of the red line. And so we have a grand mean that's still there. It hasn't gone away, but we're going to kind of focus in on the individual means now. Error is still measured the same way as the deviation of each person's measured thumb length from their predicted thumb length. But this time the error is calculated from each person's group mean based on sex instead of from the grand mean. So here they're looking at various ways of counting things, and so these people apparently are males, and we're looking at various ways of calculating stuff. And so anyway, let's take a look. On the jitter plot above, which distance is an example of error from the empty or null model? Yeah, this one kind of gets me wondering, what the heck are they talking about? They really make a big deal out of all this stuff. And frankly, this is not the way I would teach it. But it is important to see how you can put different levels together, such as gender, which is a major way of categorizing physical attributes. So in this case, we could look at the measurement from D. They're using empty model as being the overall mean. That's what they're trying to say. So D is the one, because this is the only one that seems to be attached in any great extent to the mean. I'm not sure what C is doing. It's doing like a plus and minus thing. B is going to the mean as well, but they seem to be measuring the male's difference from the mean. And A is going from the male's average. So D is the only one that seems to make some sort of sense. But that would not be a test question in my eyes, not even close. So anyway, look at the figure above. Is the deviation of y1 greater than the empty model or from the sex model? It will be greater from the empty model almost by definition, because the empty model is just trying to make a stab at it. And it may not be a very good one, but if you have everybody all averaged together, at least you got something. But if you get it a little bit more fine-tuned with the sex model, in other words, either the red line or the green line, you're going to be doing better, and the deviation will be smaller. So in other words, the way they phrase it is backwards, but yeah, the deviation will be worse, greater from the blank or overall mean model, which is what I would have called it, something else besides that. So I think I've answered the question, and you should be able to pick which one is the greater one. And yeah, there it is. Think about it. Do you think the total error would be more in the empty model? Absolutely. Yeah, we're just saying the same thing over and over again. I'd like to get on some real questions, but I'm sorry, I'm getting a little bitter here right now. Whereas the empty model was a one-parameter model, we only had to estimate one parameter, the grand mean. The sex model is a two-parameter model, a little bit more appropriate, actually. And if we had a few more, we could really fine-tune it, such as the person's height or something like that. Well, one of the parameters is the mean for the males, and there's the mean for the females, sorry, and there's a few ways you could write it, and here is just one way to do it. So we've included a little extra something right in the middle there, the B1, X1. And in this equation, Y1 is still the thumb length, E1 is, or EI, I'm sorry, YI and EI, sorry. They're both the same as before. We have the error here, and we have the thumb length here. We've got this new term in the middle. And I had to read this for a while before I finally understood what they were doing. So here I am to hopefully clarify it for you, at least somewhat. And we have the part of the equation in between them is the model part. In other words, that equals model plus error. I would never have thought of it this way, but they're thinking in a theoretical way. They're fond of this over at UCLA. And model is what this would be, the B1X1 part. And requires just a little bit of unpacking, the way they've decided to pack it up, that is. So we have to match the words to the equation, and we could say that the data is, yeah, they just said data is yi, the error, of course, is ei, and then by default, the model is what's in the middle. So they basically just said this, and they're just seeing if you're paying attention, and match words to the same thing. So they're very, very fond of this kind of stuff, and they talk about the thumb length, we just said that. The error, of course, we just said that too. And then the thumb length model's prediction, there it is, that's the model. So this is a better way to say it. I'm happy they said it this way. The model's prediction of the thumb length is right here. So that's according to whatever xi is, which they really haven't defined yet. Funny way of doing it. I would have defined my terms first, so I started jumping in. So then finally, they dive in and say, oh, what is this anyway? B0 plus B1xi is still representing each person's predicted thumb length. But in this case, the model makes a different prediction for each person. And X will happen to have something to do with the gender. But they take a little while to explain themselves, so let's see. Got the two-group model, and B0 is no longer the grand mean. Instead, represents the mean of one of the groups. Taking the shorter group would be better. So it looks like we'll pick the B0 as being the female length, and that's what they're going to eventually do. And And then they're going to add on to it if they need to. If it's a male, then we have this overage or this difference, which happens to be 6. So we start with 59 for the females. We zero it out. Let x1 equal xi equals 0 if it's a female. Do not even go here. Just use 59 plus ei. But if it's a male, then we pretend xi is equal to 1. And why do we pick 6? 59 plus 6 is 65. It's not written down. But 59 plus 6 is the average of the males. That was 65. It's not written down here. So that's how they do it. 59 for females plus 0. Females, good. If it's males, you have 59 plus 1 times 6. That gets you to 65 for the males. And then you add in whatever the error or difference would be. So this number is either 59 or 65. And that means that xi, the way they've decided to do it, is to let sometimes xi be 0 and sometimes let it be 1. Maybe I could, well, I'm not sharing the screen right now, so I guess I can't do that. So anyway, I guess I can't write like I thought. But we either have the 59 or the 65, depending whether it's male or female. And that also means that xi, as they're going to explain here in a minute, would either equal 0 for females or 1 for males, and it cannot be anything else. That's it. And xi could either be wherever they define it. So it'll be our explanatory variable, which is x and which is sex, sorry, and that reminds us that each person will have its own variable, value on the variable, and the person is either female or male. And so, as they say, finally, 0 for females, 1 for males. And when you put a 1 in, that means you grab 6 extra, that gets you to the 65. So I hope I've explained that well. This is a complicated step, which is the way they chose to do it. I've seen this done before. It's certainly not something I did a lot of, but it's possible to do it. It's called dummy coding. And there are other methods for sure. This is the one they like to use, however. Okay, fine. Let's see what would happen to predict a female's thumb length. She would be coded 0 for xi. And so the B1, whatever that is, 6 in this case, times 0 is 0. So it doesn't even matter what B1 is. It could be 10. 0 is going to wipe it out either way. So we start with typically start with the short one and build up to the large one. That seems to be a credible way to go. So based on the numbers we provided for thumb length in the tidy data set above, what is the interpretation for B sub 0? Well, B sub 0 seems to be the mean, and the mean for females, by the way. So mean for females would be what we need because that's the shorter one, and we can build upwards from there. There's nothing wrong. In fact, they'll even mention what happens if you start the other way. It's not a problem. But what is B1 going to be? That's like the difference between the two. It's the deviation from the mean of the females to the mean of the males. So actually it'd be males minus females, and that deviation is 6. But that's how they do it. They take the difference of the two, and they're not too concerned with exactly what's being subtracted from what. But the others don't even have that at all. So this is the only one that makes sense for B1, that is. So B1 is there. B0 is the mean for females, the way we've got it constructed now. Although one can make an argument for mean for males. We'll do that in just a minute. Why does the x include sub I when the parameters B0 and B1 do not? B0 and B1 are parameters. They're not changing, but x does. So we have x either equaling 0 or 1. And naturally speaking, the smallest one gets the 0 and the larger one gets the 1. And so that seems to be very natural for most people to do. And so we do have an answer for that. Parameters are the same for every single person. The x's aren't. They have only 2 choices though. So here's the new model as we've written it. 59 plus 6 times xi. They still want to use I. It'll either be 0 or 1. And then we have some sort of difference that gets you to the actual value. Whether you're on the high side of the mean for your gender or the low side of the mean for your gender, that's something that we can find out later. If we're predicting a female, what's the only value that would change in this model? Well, here we're looking at, let's see, the only one that would change would be B0. Yeah, B0 would be the only one that would change here. And yeah, so we would have that happening, and you could make a guess and see how that goes. If you're predicting a female, what would xi be? Well, as we already said, xi has to be 0, because that doesn't really allow for any extra. 59 is all you have. So 59 plus 0 plus EI. So that would have to be that one. And yeah, so I think I made a mistake back here. I was just checking, and yeah, XI is the answer to this one. That's the only one that changes. The 59 is clearly locked down. The error is depending on the individual, so XI is the only one that changes. I apologize. What I said just didn't make sense. So C is definitely correct on that. So I'll just give you that one. And for female, XI is 0. For males, it would be 6. All the others don't make a whole lot of sense. And so if you're predicting a female, what would B0 be? Well, it looks like that's going to still be, yeah, for just a blanket prediction of a female would be 59. They call that the empty model. Yeah, it's pretty empty, all right. It just says you're an average female, period. And B0, the mean, I always like to use something else for mean, but they're using B0, fine. This is a general model for the mean. So 59 would have to be your answer on that. So that's where it's D. Predicting a female, what would B1 be? Well, the B1, based on the model we're looking back here, well, let's go back even further. That would be that 6 that goes in front. That's the difference between the two. So looks like 6 would be our answer for that one. And if you're predicting a female, what would B1XI be? Well, we have to zero it out. Yeah, we have to zero it out just like we just did. So under this model, as expected, males would all end up with one predicted thumb length, 65, and females would all get the 59. Pretty boring, pretty empty, but at least we'd have 2 splits instead of just 1. So notice this does not mean that you have to code the variable in the data frame in any particular way. R does that for you. Okay, so here we have selecting an appropriate position for each term. A plus B times C plus D would be the female. And then, very similarly, E plus F, F times G that is, and then add H. And so we can fill in all the differences here. This is an extensive one, but keep all the females on one side and all the males on the other. So for the female, we have to start with the mean. So that's the 59 in this case. And then we would take the next one would be the difference between the male and female means, which was 6. And then in this case, it would be multiplied by 0 because we're starting at females being the basic number. And then we'd add in what they call D, and that's going to be the error. So error. And D and H will be the same because we have the same structure now. There's a slight difference here. Thumb length for a male would be the average mean of males, for starters, for E. And then we'll take the difference, which was the 6. And same difference as before, but this time it gets multiplied by 1. So notice there's the difference here. C and G, C is 0, G is 1. They're very, very similar. And once again, we have that same error as before. But it's very instructive for you to try this on your own. I hope my general hints helped you a little bit. How does R know to make female equal to 0? I'm sorry about the phone. I meant to unplug it. I apologize for that. The answer for this question is R doesn't know for sure. It's taking whatever groups comes first. So it's always better to pick the smaller group to be the first one and zero it out and only talk about raising the bar when you go to a larger group. Taking the next group and making it 1, the males would be a 1. And then you put the difference times 1. If you had a third group, you could make it 2 or 3 or 4. If there's many groups, you could stair step it by different routes. But we're not going to do that here, but one's plenty. A female group comes first in the variable sex because it automatically comes before male. It doesn't really matter because we could do it the other way. Just for fun, you could code male as 0, excuse me, and female as 1 in the data set. And so then you would have the mean for males, which is 62, but you'd have to then change it to -6. That's the basic idea here. Females would equal 1, but we'd have to throw it below the 62 to get down to 56, which is the mean for females in this, apparently this different data set than we had earlier. So -6, we have to deal with negative numbers. Nothing wrong with that, but you would have to do that now. You have to put a -6 in there. So it would be equivalent, completely equivalent, but most people naturally go from 0 to 1 in the same way you go from the smaller number to the larger number, whatever it may be. It just makes intuitive sense. A final note on error. We're broadening our definition of error from the way we thought of it for the empty model. Error was the residual from the mean. But now we're not going to pay too much attention to the grand mean anymore. We're going to have individual means of groups and get a better prediction. And no matter how complex our models become, our error is always defined as a residual for each data point from its predicted score under the model. So we have many choices here. And let's see here if we can figure this out. In the empty model, the predicted score, and we did say this, although not recently, we do have a hat that is a prediction. And we're interested primarily in y, so y hat looks like the answer there. And that would be the grand mean. Grand mean has a bar. We're not talking x's quite yet, so put a bar over the y bar. But in the gender model, where we split it up, the predicted score, which is still going to be a y hat, so these two are the same. Predicted is always with what they call a hat, a little arrow on it. That's meant to be a hat. And then the mean of female group or the mean of the male group, either way. And so depending on which one we're going after, and we would have to amalgamate that, so this is the tough step, as B0 plus the difference B1 times that 0, 1 variable. 0, you leave it alone, basically just cross this out. 1, you keep it and put that difference back in, multiply by 1, say like 1 times 6 that we saw already, and that gives you the difference that makes it a male guess, male prediction versus a female prediction. I wish I could write on the screen. I'm just not able to figure that out right at the moment. I'm sure it's really easy. I just don't know how to do it. So you have your basic, say, female prediction, and then you put in, as we already did before, 0 or 1 into the x, and here is the difference between the two mean-wise. So a difference of 6, for example. Either you put it in or you don't. You either 0 it or you 1 it, and that includes it or not. So this is the way they put it, the mean of the female group, the mean of the male group. This is quite different than the way I would teach this class, but this is what we have going for us. I've been teaching stats ever since, well, many, many years ago, before most of you were probably born, and this is a completely different way of teaching it. Yes, I am familiar with all this stuff. Did I ever really deal with it very much? Not particularly, but this is the way they want to teach it. So this is what we got for you. Don't blame the messenger here. I'm just trying to do the best I can to help you understand this stuff. Please do this stuff in advance if you can. Don't depend on me too much. Be sure you're doing the chapter quizzes, trying to learn something from them. Hopefully you're getting like at least a 70 as you try them. But if you're not, try to figure out why. Try to make sure you got the correct answers and learn from your mistakes. That's the biggest part. Everybody will make them. Almost nobody will be perfect on this the first time through. I know I'm not. And just do the best you can and try to learn from them. Do not skip the chapter quizzes. Please don't do that. That would be a big mistake. So you got to take them, and who cares what your score is? The test counts just a little bit more than the quiz does. So please put that in perspective. Some people say, oh, they're the same. Oh, no, they're not. I don't have my syllabus right in front of me, but is it around 25% of the grade as compared to 1 or 2% of the grade? Yeah, you figure it out. There's a big difference there. You're supposed to learn from the quizzes, and hopefully the learning will be already taken care of by the time you take the test. But yet the test is still a learning experience, although hopefully you've already learned quite a bit by the time you take it. And learning for the final, though, for sure. So yes, you'll be learning from the test to learn for the final. I guess that's about all I have. Yes, we will have a live lecture on Wednesday, Thursday. The test will be on the 9th and 10th. If you haven't voted, please go out and vote and see how that goes. And happy Halloween. Of course, by the time you see this, it'll be past already. So with me, I'm still recording on Friday, so it hasn't happened yet. Okay, I guess that's all I have. And take care, and please email me if you have any concerns or questions, and we'll talk to you soon. Bye-bye.